YouTube is flooded with videos titled How I Would Code If I Could Start Over, and most of them have between 100,000 and 1 million views, thanks to YouTube's unbiased algorithm. It seems to be a bandwagon that every software engineer YouTuber has jumped on. Don't get me wrong, these videos are very interesting and impactful, and hence why they're so popular. But what I noticed is there are very few videos like these for mechanical engineering, so I'll be filling in this void to help any of you thinking about getting into or currently studying mechanical engineering to 1, better learn the engineering curriculum material, and 2, land more jobs. There are 2 aspects of learning mechanical engineering that you should be aware of. The first part is the engineering curriculum and the related material you need to learn, and the second part is the knowledge and skills you need to land your dream engineering job. I want to emphasize here that the bodies of knowledge you need to do well in your engineering courses are quite different than the bodies of knowledge you need to land jobs, but there is also, of course, overlapping knowledge that you need to do well in both areas. For example, you will need to know what the intermediate value theorem and Green's theorem are to do well in calculus class. But these are actually useless when it comes to passing engineering job interviews or engineering actual products in real life. So the useful material taught in most mechanical engineering curriculums include the more theoretical classes like mechanics of materials, material science, thermodynamics, heat transfer, and fluid mechanics. The practical classes include manufacturing processes and electromechanical design. Mastering the material taught in these classes is important because it's fundamental knowledge that every mechanical engineer who designs products and processes should know and will help you pass more engineering interviews. Now, while having this fundamental knowledge is a great starting point, it doesn't really guarantee you'll get your dream job because you really never know what the interviewer is going to ask. So later in this video, I'll talk more about this and how you can pass more engineering interviews in general. So let's begin by talking about the essential engineering topics that are commonly asked in job interviews and that you should focus on as a student. We'll start with the theoretical classes, the first being material science. Important topics that you should know include the structure and properties of materials including metals, polymers, ceramics, and composites. For example, the structure of polymers is either amorphous or semi-crystalline. Thermoplastic polymers can be melted and reused, while thermoset polymers do not melt when heated. You should also be familiar with different types of engineering plastics such as polycarbonate, ABS, polyethylene, PLA, and PEEK. Expect to be asked about some of these materials in a job interview, including their material properties and applications. Metals, on the other hand, have a more well-defined crystalline structure, including body-centered cubic, face-centered cubic, and hexagonal closed pack. When it comes to metals, you should be familiar with the various types of heat treatments and strengthening mechanisms used to enhance their mechanical and chemical properties, such as strength and hardness. Common heat treatment techniques include annealing, quenching, tempering, and precipitation and case hardening. Strengthening mechanisms at room temperature include cold working, work hardening, and grain boundary strengthening. A phase diagram is often used by material engineers to understand how metals and plastics behave at different temperatures and pressures. Composites, on the other hand, are made by combining 2 or more material types. There are metal matrix composites, plastic matrix composites, and ceramic matrix composites. The most popular composite is probably carbon fiber, which offers superior strength, durability, and lightweight properties. They're used in automotive and aircraft components, as well as this fancy, stylish wallet by Exter, the sponsor of today's video. Exter is the leading maker of smart minimalist wallets, offering top-notch quality, a futuristic design, and cutting-edge RFID blocking technology. Exter wallets are ultra slim, freeing you from the burden of traditional bulky wallets, and come in a wide variety of colorways and materials. One of my favorites is their carbon fiber wallet made from 3K space-grade carbon fiber, commonly used in aircraft fuselages, so the wallet is extremely light and will last for ages. You can fit up to 6 cards in this slot and additional 6 cards in this back plate for a total of 12 cards. You can also hold your cash in the front with the rubber band. All of Exter's wallets feature a trigger mechanism at the bottom for easy access, so you're always ready to pay no matter how fast life moves. If you're a fan of leather wallets, Exter's got you covered. This is the Parliament, which is Exter's stylish flagship wallet made from premium, environmentally friendly leather that features an aluminum card holder and can hold up to 12 12 cards. I partnered with Exter to give you guys an exclusive discount. Get 25% off now through my personal link or code EGW listed in the description below. Let's move on to the next class, mechanics of materials. One of the most important topics covered in this class is the stress-strain curve. This is a graph that shows the relationship between stress applied to a given material on the y-axis and the resulting strain it undergoes on the x-axis. Stress is a measure of how much force that's being applied per unit area, while strain is the amount of deformation the material undergoes when subjected to stress. This graph will look different for each material and is obtained by stretching or compressing a piece of material in the shape of a dog bone on a universal testing machine. Engineers use these curves to select materials for a new product to ensure that it can withstand the mechanical forces that it will encounter in its in-use application. For example, surgical sutures must have enough strength to hold living tissue together. Many engineering interviews will ask you to explain or draw this diagram, so it's good to be familiar with all the points and regions on it. The curve can be split into the elastic and plastic region at the yield point or yield strength. If I apply a stress that's below the material's yield strength, it will return to its original shape and stay within this linear region. The slope of this line is the Young's or elastic modulus represented by E, and is the ratio of stress to strain within the elastic region. The higher the value, the more stiff a material is. Any stress exceeding the yield strength will cause the material to permanently deform, which is this nonlinear area known as the plastic region. The peak of this curve represents the ultimate strength of the material, which is the max stress a material can handle right before breaking. Finally, this point is called the fracture point, which is the stress at which the material breaks. The stress strain curve for brittle materials will look something like this, and for ductile materials, it will look something like this. You should be familiar with the stress-strain curve and what the elastic modulus is for common engineering metals and plastics such as steel, aluminum, and polyethylene. Now, a material can experience various forces and moments. The ones you should know include axial loading, which includes tension and compression, torsion, and bending. When a beam is bent, you will use the flexure formula to calculate bending stress acting on it. Sigma equals negative my over I. Sigma is the bending stress represented by these blue arrows, m is the internal bending moment, y is the distance from the neutral axis, and I is the moment of inertia. The formula for moment of inertia will depend on your cross-section geometry and location of the neutral axis. In this case, it's a rectangle with the neutral axis passing through the centroid, so we have I equals bh cubed over 12. B is the width and h is the height. Aside from the flexure formula, you should also know the deflection equation for a cantilever beam, which is a beam that has one fixed end and one free end like this. To calculate the deflection, when a force is applied at the free end, you can use this equation. Delta equals FL cubed over 3EI. F is the applied force, L is the beam length, E is the Young's or elastic modulus that we saw earlier in the stress-strain curve, and I is the moment of inertia that we saw in the flexure formula. This deflection equation is specific for this beam configuration and will be different if the location of the applied force changes or say the beam is fixed on both ends. For some reason, engineers have this weird fascination with beams, so expect to get asked about this equation in a job interview. With these two formulas, you should know how to calculate the maximum and minimum deflection and stress and where along the beam they occur. Next is thermodynamics and heat transfer. These were separated into two courses at my school, and they're both equally important. While thermodynamics is a broad branch of physics dealing with the behavior of energy and matter in physical systems such as a rocket or refrigerator, heat transfer deals with the mechanisms and rates at which thermal energy is transferred from one object to another. There's a lot to know about thermodynamics, but for now, start off by understanding the 4 laws of thermodynamics. The 0th law states that if objects A and B are both at the same temperature as object C, then object A and object B are also at the same temperature with each other. The first law says that energy cannot be created or destroyed in an isolated system. It can only change forms. In other words, the total energy within a closed system remains constant. The first law can be represented by delta U equals Q minus W, where delta U is a change in internal energy, Q is the heat added to the system, and W is the work done by the system. The second law of thermodynamics introduces the concept of entropy, which is a measure of the disorder or randomness in a system, and says 3 things. The first is heat flows from a hotter to colder object. The second is it's impossible to create a heat engine with 100% efficiency. And the third is the total entropy of an isolated system always increases over time. Finally, the third law states that it's impossible to reach absolute zero or negative 273.15 degrees Celsius using a finite number of steps or processes. Finally, you should understand the different thermodynamic processes and their applications like isothermal, isobaric, isochoric, isentropic, and adiabatic. Take a rocket, for example. Fuel and oxidizer are mixed and burned, which results in higher temperature and pressure gases in the chamber. The process by which the gases expand as they pass through the rocket nozzle to generate thrust should be adiabatic. For heat transfer, there are a lot of equations, but don't worry too much and start off by understanding the three modes of heat transfer: conduction, convection, and radiation. Conduction is when heat is transferred in an object or between two objects in contact due to a temperature difference and is represented by Fourier's law. Q dot represents the heat transfer rate, K is the thermal conductivity, which is a material's ability to conduct heat. For example, the thermal conductivity is excellent for copper and not so much for wood. A is the object's cross-sectional area, T1 is the temperature of the hotter end, and T2 is the temperature of the colder end, and L is the distance between them. Heating up a pan is an example of conduction. Convection is when heat is transferred by the movement of a liquid or gas and can be represented by Newton's law of cooling. Q dot is the heat transfer rate. H represents the convective heat transfer coefficient, which quantifies a fluid's ability to transfer heat. Water, for instance, is better than air at transferring heat. A is the surface area, T is the temperature of the object's surface, and TE is the temperature of the environment. An example is water boiling. Finally, radiation is when heat is transferred in the form of electromagnetic waves. All objects that you see emit thermal radiation even if it doesn't feel warm. It can be represented by the Stefan-Boltzmann law, where Q dot is the heat transfer rate, epsilon is emissivity, which quantifies how effectively an object emits thermal radiation, sigma is the Stefan-Boltzmann constant, T is the temperature of the radiating surface, and Ts is the surrounding temperature. An example is the sun heating up the earth or warming yourself up with an electric heater. Now let's talk a little bit about fluid mechanics. Now I can sit here and talk about the concepts and equations from this class all day, but if I did that, this video will be several hours long. So I'll briefly mention three important concepts that you should definitely know. First is the continuity equation that describes the conservation of mass within a fluid system. Assuming the flow is steady and incompressible, it can be represented by A1 times V1 equals A2 times V2. A1 and A2 are the cross-sectional areas at point 1 and 2 in, say, a pipe or tube. V1 and V2 are the velocities at points 1 and 2. Second, you should know about Bernoulli's equation that describes the conservation of energy for a fluid. Assuming that the flow is steady and incompressible, we can apply the equation to a single streamline in a fluid where P1 and P2 are pressures at points 1 and 2, V1 and V2 are velocities at points 1 and 2, and H is the height at points 1 and 2. Rho is the fluid density, and G is the gravitational acceleration. This equation can be used to analyze flow across an aircraft wing. Finally, we have the Navier-Stokes equation, which is a set of partial differential equations used to describe the velocity field in a fluid throughout space and time, and accounts for effects of pressure gradients, viscous forces, and gravitational forces. P is the pressure, V is the velocity, mu is the dynamic viscosity, rho is the fluid density, G is the gravitational acceleration, and inverted delta represents divergence, which just takes a vector field to produce a scalar quantity such as pressure or velocity. Moving on to the more practical classes, we have manufacturing processes. This class is very important because you learn about how different parts are created using a variety of manufacturing methods based on the part design, part material, annual volumes, costs, and lead times. The most popular one that engineers use are CNC machining, injection molding, sheet metal forming, and 3D printing. CNC machining is a subtractive process that leverages milling machines and lathes programmed with G-code to generate generate tool paths and precisely remove material from a piece of plastic or metal raw material to create complex features and shapes. Injection molding is great for high volume applications that takes plastic pellets and loads them into a hopper. As the plastic pellets are pushed forward by an auger, they melt and the molten plastic fills a mold cavity where it cools, solidifies, and is ejected from the mold core by ejector pins. The part is finished and the process repeats all over again. Without injection molding, we would never come to know the wonders of Legos. Sheet metal forming is when you take a flat sheet of metal, deform it by applying a force using various methods such as bending, stretching, and stamping. Car door panels, for instance, are made with this process. Engineers rely on 3D printing to make prototypes and even low-volume end-use parts. To 3D print a part, engineers will take their 3D CAD model and save it as an STL file where the 3D model is sliced into very thin horizontal layers. The printer adds one layer on top of another following the instructions from the sliced file, and the material cools and solidifies after being extruded from the nozzle. Most 3D printers print in plastic, but there are also metal and ceramic ones. The material is usually in the form of a spool of filament or powder depending on which technology the printer uses. The most popular ones are FDM, SLA, and SLS. If your part has complicated features like overhangs or undercuts, the printer will add temporary support structures like these that can be removed after the print. As an engineer, you should be well versed in design for manufacturing or DFM principles. For example, if you're designing a CNC milled or plastic injection molded part, you will need to apply the rules of thumb and design guidelines for each particular manufacturing process. In a nutshell, a plastic injection molded part should consider things like uniform wall thickness, draft angles, undercuts, and material shrinkage rates, while a CNC milled part should avoid deep, narrow features, sharp corners, custom hole sizes, and threads. If you look at any well-designed product, take this iPhone for example. Hundreds upon thousands of iterations and prototypes for each component were made and tested. To build these prototypes, you will need to know how to use some essential tools and machinery. Hand tools include calipers, hand drills, Allen keys, screwdrivers, impact drivers, and deburring tools. Equipment and machinery that are good to know include CNC machines, 3D printers, drill presses, bandsaws, bench grinders, welding machines, sheet metal machines, injection molding machines, soldering irons, multimeters, and oscilloscopes. Saving the best for last, we have electromechanical design class. This class equips you with practical skills that make you employable. First, you should become an expert at using at least one CAD software to design parts such as SolidWorks, Creo, CATIA, NX, Inventor, or Solid Edge. Most of these offer student editions, so just pick one to learn and practice modeling anything you can find. There are plenty of tutorials on YouTube to help you get started. Mechanical engineers use CAD to design 3D parts and assemblies of actual products, as well as to make 2D technical drawings so that these parts can be manufactured according to engineering specifications. For every part you design in class or for a club, think what manufacturing process you would use to make it and how you can optimize part design to improve manufacturability and cycle time without sacrificing functionality and performance. Now, even though we're mechanical engineers, virtually every product in the real world, such as iPhones, robots, aircraft, and cars, involve moving parts and electronics. So another valuable skill that you should have is building simple circuits using breadboards and knowing how to program microcontrollers to control sensors, motors, valves, and lights. Familiarize yourself with different types of brush and brushless motors, encoders, and sensors. If you want to get started, I highly recommend getting an Arduino or Raspberry Pi kit on Amazon. Link in the description below if you're interested. Now, once you step foot in industry, you can't just go up to a machinist or your manufacturer and say, hey, here are the CAD models of all the parts I just designed. Make them for me. They will basically wipe you off the face of this planet if you do that. So instead, as an engineer, you need to make professional 2D technical drawings that follow ASME Y14.5 GD&T standards. GD&T stands for Geometric Dimensioning and Tolerancing, and it's the universal language for communicating tolerances and geometries on a drawing. There are 14 symbols in total that describe how flat a part surface must be or where a slot or hole feature must be exactly located. You should know what all of these symbols represent and when to use datums. For example, if I called out this flatness symbol for a part surface, the final surface must fall between these two blue planes parallel to it. One that's 0.03 inches above and another one that's 0.03 inches below it. A quality engineer or a technician will use a CMM or OMM to check if the part meets this specification. Now, before engineers send parts off to be produced, they first need to perform a tolerance stack-up analysis to ensure all of the parts will fit together seamlessly based on the tolerances called out on the drawing. Tolerance is the allowable amount of variation of any given part dimension. Types of tolerances you can call out include limit, unilateral, and bilateral. For every dimension on a drawing, ask yourself if it's critical and if you can get away with calling out a standard tolerance of 5/1000ths of an inch, or do you need a super tight tolerance of 2/10,000ths of an inch based on the part's function. Inexperienced engineers tend to over tolerance, which can drive up part and tooling costs and drive down yields. There are 3 kinds of tolerance stack-up analysis, and they are worst case, root sum square, and Monte Carlo. Understand the pros and cons of each and try doing a calculation using Excel or 3ds. Okay, so these are some of the things I would focus on if I could start over and go back to university to relearn the material. By no means is it an exhaustive list, but as an engineer, you'll be in a very good spot if you work on understanding the theoretical concepts and developing the practical skills that we just covered. As much as I hate to say this, knowing these things cannot guarantee that you will pass engineering interviews and land your dream job. It'll definitely help, but it doesn't guarantee anything. That's just the hard truth. Now, I want every single one of you to land your dream job. So if there's one thing I wish I knew before interviewing for all of these jobs, is a systematic way to prepare for these interviews. First, I will research everything about the company I'm interviewing for, their products, competitors, history, mission, and growth strategy. Second, I will know my resume and job description inside and out. Because engineering managers love to kick off interviews by going through the projects and qualifications listed on your resume before getting into the meat of the technical questions. Now, the hardest part about mechanical engineering technical interviews is you never know what the interviewer, who could be an engineer, engineering hiring manager, or a panel of engineers, will ask. Mechanical engineering is a very broad discipline, and technical questions tend to either be very specific or have to do with challenges that the company is currently facing. So you would only be able to answer these questions if you've done a ton of technical interviews in the past or worked in industry as an engineer for a year or 2. Unlike coding technical interviews where questions are transparent and available on platforms like LeetCode and AlgoExpert, mechanical engineering questions are a wild card and way harder to prepare for. The technical interviews always seem to trip me up as a student in university, so I learned everything the hard way through trial and error. To help you guys out, I put together a list of 80 technical practice questions spanning all areas of mechanical engineering that I think are great to know, and hopefully it will help you land your dream job. So if you're interested, check out the link in the description below. Now, to summarize, if I had the choice to study mechanical engineering again, there are 2 components I would focus on. Number 1 is understand the material from these theoretical and practical classes, which will help you become a well-rounded engineer and prepare you for the job hunting and interview process. Number 2 is research everything about the companies you are interviewing for and analyze your resume and job description to get a good idea of the questions that you might get asked during an interview. Alright guys, that's all I have for you today. As always, thank you so much for watching, and if you found this video helpful, check out my video here where I talk about everything you need to know before getting into mechanical engineering, and I'll see you in the next one. Peace.